Hello everyone, I'm Shiyao from the Department of Electronic Engineering in Tsinghua University, and I'm glad to be here to introduce our new work, TCP, Triplet Contrastive Relationship Preserving for Class-Incremental Learning. First, I will introduce the background. Let's see the difference between human and a neural network in continuous learning. For human, we learn new knowledge in a dynamic style. Only the new category of data are needed, and the new synthesis can be built dynamically. Without the data of the old category, the classification performance of the old category can still be retained. However, for NNs, they learn new knowledge in a static style, which is difficult to learn the new knowledge while keep the old knowledge. Next, let's talk about the definition of continuous learning. Well, for dynamic scenarios, only new data can be accessed when learning new categories. Well, the aim is to maintain the task performance in both old and new categories. Well, continuous learning focuses mainly on two aspects. The first is the plasticity, the ability to learn new tasks well and achieve ideal performance on new tasks. The second is the stability. Well, this is the ability to keep old knowledge from being forgotten, and this is often caused by catastrophic forgetting for tasks, which is very difficult. Well, learning on data of new classes without accessing old data causes the DNN to forget old knowledge, like this, which is known as catastrophic forgetting. Well, a naive approach is to retain the full version of the old dataset and train the DNN on all of the old and new data. Well, nevertheless, this is inefficient and even impractical in terms of memory constraints or some privacy constraints. Well, to facilitate an effective CIL learner, we focus on two questions. The question one is what type of knowledge in the old model should be preserved? Well, existing works focus on the new model to output similar feature in the sense of exact value as the old model, as we can see in this figure. Well, learning new classes can change the optimal feature space and hinders the learning of new optimal feature space. And the question two is how to adapt the feature space to the new data, as shown in figure B and figure C. There are much fewer data in old classes than in new classes. Well, directly apply the old and new data would learn the suboptimal feature map. Well, so our motivation to solve the above two issues is here. Well, to preserve old knowledge, we aim to find the invariant feature during learning. Well, we find that the order of the cosine similarity remain unchanged. Well, like this figure here. Well, we find that over 77% of the sample triplet can keep the original order after learning new data, which is here R1 greater than R2 and greater than R3, and after learning, well, it also keeps the same order here. Well, the second one is to adapt new knowledge. We focus on addressing the class imbalance problem, which introduce an asymmetric data augmentation strategy to add more complex augmented old data to address this issue. Well, second, I will introduce our method details. Well, we first introduce our method overview. Here, the first is our method. We use asymmetrical augmented contrastive learning to learn new classes, and we use the triplet contrastive preserving to preserve the old knowledge. This two part is very different from the original learning style, like pointwise distillation methods for continual learning. Well, first component is the triplet contrastive relationship preserving loss. Well, we adopt the triplet-wise TCP loss to preserve the samples relationship. Well, this loss it enforces the consistency of the triplets contrastive relationship between the old model, which is R1 greater than R2 and greater than R3. Here the R is the cosine relationship. Well, and the new model, which is also keeps the same order. Well, we formulate the triplet contrastive relationship loss to preserve the order of the relationship. Actually, we use the triplet loss to achieve this purpose. Well, the second component is a symmetrical augmented contrastive learning. Well, to adapt the feature space to learn new classes, we employ the supervised contrastive loss to learn the relationship representations from the perspective of contrastive relationship optimization. Well, in order to alleviate the imbalance issue, which we can see here, well, the blue one is a new class, and the green one is a new class, and the blue one is the old class. We can see the old class have only a few samples here. Well, to make the old data more complex, we use strong data augmentation on old classes to produce more old samples, and we use the weak data augmentation on new data here in SCL, instead of using a simple augmentation for all exemplars, including the old and the new. Third, I will introduce the experimental results. Well, for the main results, the TCP outperforms the recent SOTA pairwise distillation and the SOTA pointwise distillation on CIFAR and ImageNet. In addition, as our method can be easily plugged into other methods, we also plugged our TCP into RMM, and in this case, we can also surpass the model expansion methods like DER. Well, comparison with the distillation loss, while keeping a similar accuracy on old class, our TCP loss can significantly improve the new data performance, as we can see here. And we also show that applying an asymmetric data augmentation strategy is useful to alleviate the imbalance between old and new class. Well, as we can see, when applied the A2CL, our average accuracy is larger than any others. Well, finally, we also found that our method is very, very useful when only use a small memory buffer. As we can see, less than 10 exemplars per old classes. Well, this means our method is superior for extremely storage constrained scenarios. Well, thank you for your attention. That's all of my presentation. If you have any question, please